Have you ever wondered how a pilot figures out the exact flight path in a heavy crosswind, or how a game developer knows precisely where a thrown object will land? Well, those are vector problems. And today, we're going to unpack the most powerful and precise way to solve them, the analytical method.
Think about it like this. If you take one trip and then you take another one right after, where do you actually end up? How far are you from where you started and in what direction? That's really all we're doing when we add vectors, just finding the final result of combining things that have both a size and a direction. It's super easy when everything's in a nice straight line. You walk 5 kilometers east, then another 3 kilometers east. Boom, you're 8 kilometers east. Simple. But what happens when those paths go off in different directions? All of a sudden, 5 plus 3 definitely doesn't equal 8 anymore, and that is the challenge we're tackling today.
So, how do you even begin to solve this puzzle? Well, the first thing most of us would do is just draw it out, right? Grab a ruler, a protractor, and just map it. And for a rough idea, that's great. But for anything that needs to be truly accurate, drawing has some pretty serious limitations. You can totally draw one arrow, then draw the next arrow starting from the tip of the first one. We call it the head-to-tail method, and it gives you an awesome mental picture of what's going on. But for science, for engineering, for anything that really needs to be on the money, a shaky hand or a thick pencil line just isn't going to cut it. We need something better. And that brings us to the real hero of today's story, breaking vectors down into their components. This is the truly precise way to do it. It lets us trade in our clumsy rulers and protractors for some clean, simple arithmetic. So here's the big idea. Instead of wrestling with all those weird angles, what if, and hear me out, what if we could translate every single one of those diagonal vectors into a simple pair of instructions, one that's purely horizontal and one that's purely vertical? And that's exactly what components are. They're just the pieces of a vector that point perfectly along the x and y axes. A good way to think about it is like they're the shadows the vector casts. One shadow on the ground, which is your x-axis, and another on a wall, your y-axis. You add those two shadows together, and you get the original vector right back. The classic city block analogy really makes this whole thing click. Imagine you're taking a diagonal shortcut across a park. You'll end up in the exact same spot as someone who sticks to the sidewalks, walking, say, 9 blocks east, and then turning and walking 5 blocks north. Those two separate paths, the east part and the north part, those are the components of your diagonal shortcut. Okay, so the city block idea is a great visual. But how do we find the exact lengths of those blocks using math? Well, for that, we bust out our precision toolkit, basic trigonometry. Remember good old SOHCAHTOA from math class? Believe it or not, that's all we need. All right, so to find the horizontal piece, the x component, the formula is super simple. You just take the total length of the vector, we call that its magnitude a, and you multiply it by the cosine of its angle theta. That's it. That gives you the east-west part of your journey, exactly. And for the vertical piece, the y component, you guessed it, it's pretty much the same deal. You take that same magnitude a, but this time you multiply it by the sine of the angle, and that gives you the north-south part. Let's make this real for a second. Let's say we have a force of 15 newtons pulling something at a 60-degree angle. The horizontal part of that pull would just be 15 times the cosine of 60 degrees, which is 7.5 newtons. And the vertical part? That's 15 times the sine of 60, which comes out to about 13 newtons. See? It's literally just plugging numbers into the formulas. And here's the really beautiful part. Take a look at these different vectors. It doesn't matter if it's pointing up and to the right, or down and to the right, or any other direction. The exact same math works every single time. Your calculator even does the heavy lifting and gives you the correct positive or negative signs to tell you if a component is going left, right, up, or down. It's so cool. So now we've got the tools to break any vector apart. The next big step is putting all those pieces back together. We can do this with a really simple process. Just resolve, sum, and then rebuild. This right here is the whole game plan, all in 5 steps. Step 1, break down every single vector into its x and y components. Step 2, add up all the horizontal, the x components, to get one total. Step 3, do the exact same thing for all the vertical, y components. And guess what? The hard part's over. Steps 4 and 5 are just about building a single, brand new vector from those two totals. Okay, let's put this into practice. Imagine we have 2 different walks.
Vector A is a walk of 53 meters at a 20-degree angle. Vector B is a walk of 34 meters at a 63-degree angle. What we want to find is the total displacement, that single straight-line trip from your starting point to your final ending point.
This table just lays it all out perfectly. For vector A, the x component is 53 times the cosine of 20, which is 49.8. The y component is 53 times the sine of 20, which is 18.1. We do the same thing for vector B. Then, the magic happens. We just add the x's together to get our total rx, and we add the y's together for our total ry. That whole tricky diagonal problem, it's just simple addition now. How cool is that? All right, time to rebuild. Our two totals, rx and ry, actually form the two sides of a right-angled triangle. So to find the length of our final vector, which is just the hypotenuse of that triangle, we use the good old Pythagorean theorem. A squared plus b squared equals c squared. We crunch the numbers, and it gives us our final magnitude, 81.2 meters.
But wait, a vector isn't complete without its direction, right? So we go back to our trig toolkit one last time. Remember SOHCAHTOA? The TOA part tells us that the tangent of our angle is the opposite side, that's our y, divided by the adjacent side, our x. So we just pop that fraction into the inverse tangent function on our calculator, and it spits out the angle for us, 36.6 degrees. And there you have it. The sum of those two different walks is one single final vector, 81.2 meters at an angle of 36.6 degrees. It's precise, it's accurate, and we did it all with a calculator. No rulers, no protractors, nothing.
So why does all this matter? I mean, this isn't just some clever math trick. This method is absolutely fundamental to how we describe the physical world all around us.
I mean, just think about pulling this desk. When you pull it at an angle, part of your force is actually pulling it forward. That's the x component. But another part of your force is also lifting it up just a little bit. That's the y component. Understanding these components is absolutely key to figuring out how things actually move. And this idea scales up. I mean, way up. As this quote from our source material points out, meteorologists use this exact same logic, just in 3 dimensions, to model how the air in our atmosphere moves, to predict the weather, even to track things like hurricanes. The wind itself is a vector, and its motion is governed by these very principles. So we've totally mastered adding vectors by breaking them down and building them back up. But this same logic opens up a whole new world of questions, like how do you subtract a vector to find a change in velocity? And what could it possibly even mean to multiply 2 vectors? It turns out there isn't just one answer, there are 2. But that, well, that's a story for another